So to give you some sense of why the second projection operator splits a space, I'll take a stupid little example and just work it by hand. I won't do it for dihedral group 3. You can check this in notes, but I'll just take, somebody has given you some Hamiltonian for some reason, and that Hamiltonian says, this spring couples to this spring or whatever they do. And I've constructed a particular kind of mattress, and you're supposed to find its eigenmodes or eigenfrequencies, and they should be all orthogonal to each other, and you should find the energy, the kinetic plus potential energy of the thing in the irreducible representations. The thing that we did first a week without using group theory. So that's a typical calculation where I find projection operators useful. So here is an example where I have two commuting observables. So here is a matrix M. The matrix is kind of nice because it's symmetric. So, if it were Hermitian, complex conjugate will be the same because it's real, just symmetric. So that's a good idea. Okay, and you look at it, I immediately see that there is an eigenvalue, which is 3, because there is a block like that, another block. So I already know one eigenvalue. If I look at the block that actually has 2 eigenvalues, this is just a quadratic equation to compute eigenvalues, so I'll trust that you will believe me. And I'll call them lambda 1, lambda 2. And they turn out to be 1 and 3. So we have 2 distinct eigenvalues. Which tells me that according to our formulas, I can use this matrix to subdivide space into 2 spaces, because once subspace, the M will return value 1. But on the 2-dimensional subspace, it will return the eigenvalue 3. So now, I'll go explicit. For the first eigenvalue, I have matrix minus 3 over the eigenvalue 1 minus 3. And if I write it out, I can see, so, all I've done is I've taken this and I've subtracted for 3 times the diagonal. That got rid of this point, and I can see that I have a rank 2 matrix. I have zeros elsewhere. So now if I take a trace of this, I get 2 from here divided by 2. So this is 1D space. And, the eigenvector, I can read it off for this space. Let's call it 1. So it's a vector that has 3 components. But, it's either a column or a row of this thing. It's very easy to figure out. Now, the other space, P2, that's eigenvalue corresponding to 3. I get 3 minus 1 downstairs. minus 1 that corresponds to this space. This is 1/2 of 1, 1, 1, 1, 0, 0, 0, 0, 2. Now, the dimension of this space, subspace, is 4 on diagonal divided by 2, so it's 2-dimensional. And this 2-dimensional space, I can easily write 2 eigenvectors. These are not normal, these are not unit vectors. One of them looks something like this, and the other one looks something like this. So they're orthogonal to each other. They're orthogonal to the third one, but this is an invariant subspace of this dimension. So that's how an example of if I have a single observable, it will split the space in 2 ways. And, it's not totally obvious because they're repeating eigenvalues when you do this, etc. But it basically splits it into 1-dimensional space and 2-dimensional space, and they sum to 3 dimensions. So this is just, like being an engineer. Are you okay? Now, Bo comes in and says, yeah, but I have a different experiment to do. So there is a second observable. It's also a nice one. It's Hermitian, but in my coordinates, and the second guy looks like this: 3, 3, 3, minus 1, minus 1, minus 1, minus 1. Now, obviously, on 1-dimensional spaces, there'll be no reduction. So obvious that n acting on 1-dimensional space, the first one, if I just multiply these 2 matrices, I have it here, I'll just get 4 times P1. So 1D space cannot be split further reduced. I also have a 2-dimensional space. So if I multiply n and look at it on projection on the 2-dimensional space, the projection operator for 2 dimensions was, this is the matrix 3, 3, minus 1, minus 1, minus 1, minus 1. And the projection operator was this matrix here. And you just multiply it out. I've done that already. And I get something. Now it turns out that's the same if I multiply it in the other order. So that means that my original observable M and N are commuting, which you can check. So now it's possible that this new thing does something to the two-dimensional space. The one that we're looking at it right now. And indeed, if I compute n square, so let me call this combination observable on the second space. On the one-dimensional space, it's just 4, but on the second space, it's actually some kind of matrix. Does this matrix have a characteristic equation? To find that, I take a square of it, see where I get something interesting. So, it's this thing squared, and you chug along, or let Mathematica chug for you. And the result of squaring this matrix, which is multiplying other rows, is a matrix like this. And that matrix, you observe, can be written as Pn2 minus 4 P2. But P2 is projection operator on the space. So it means that I have an equation that says N2 square minus 5 n plus 4 times identity on the subspace P2 equals 0. So
n square times, or is it n2 square times?
It's all n2. This comes from here, this comes from here, and this comes writing it as 1 times the multiplication, because because I'm on a subspace, I have that n2 p2 equals n2 by the definition, right?
Okay. Got it now.
Everything. But now I've written it as a polynomial equation on the subspace. This equation I know how to solve. This is n minus 1 times, and because I have this projection operator, you can just call it n, doesn't matter. This suffix doesn't really matter. N minus 4 on this subspace. So I know the eigenvalues of this guy. So let's call them lambda 4, because we used all the lambda 1, 2, 3. One of them is 1, and the other one is 4. So this new observable has its own projection operators, 2 of them. There's now a P4 operator that corresponds to eigenvalue of this guy equals 1. It's a quadratic equation, so when I remove one term in this product, I just have one term left. So it's n2 minus 4 times identity. 1 minus 4 equals 1/3. Now, you have explicit form of this matrix. So you know how to subtract 4 on diagonal. And this is negative downstairs, and you get a very simple answer. And then there is the other guy corresponding to eigenvalue lambda 5 equals 4. So this is n2 minus 1, 4 minus 1. And this is 1/3. And now when you subtract these guys, you get zeros on the diagonal of some, do you? So these are two projection operators. They're mutually orthogonal. And they have eigenvectors. Eigenvector. This one has, simple eigenvector 1, 1, 1. And this one has eigenvector 1, 1, minus 2. And now what happens is that acting on that space, you have gotten two new spaces. The dimensions of the spaces are the traces of these matrices. So here I'm not using regular representation or any such voodoo. Trace of this thing is 3 divided by 3. Yeah, my problem is I should have I have to multiply this by the projection operator 2, P2 times P2, which I haven't done. But basically, once you do that, you'll get also one dimension. So now we have 3 irreducible one-dimensional subspaces. And in terms of these projection operators, now we have 5 projection operators. But the n, in terms of its projection operators, is the eigenvalues it has, because remember, n had second observable had eigenvalues 1, 4, and so spectral composition of this thing on their subspaces are 1 plus p1. In these coordinates given by the irreducible operators, we have that m looks like this in terms of this operators. This one looks like 4, 1, 4 in the 3-dimensional space, but now diagonalized. And you can see that if I start with irreducible subspaces of M, this is a 2-dimensional space, but the next measurement, they're both diagonal, so they obviously commute, splits it into 2 subspaces. If I started with irreducible subspaces of N, then I have 1-dimensional space and 2-dimensional space with eigenvalue 4. But the next measurement returns 1 and 3 and splits it into 1-dimensional subspaces. So here is an example where having 2 commuting observables reduced a 3-dimensional representation to 3 1-dimensional representations. So that's sort of the spirit of working with projection operators. They're really hands-on. I'm not using any character tables, etc. I just do the calculation in terms of projection operators. Now, there's much more. I'll give you the chapter from Harter's book. He has it online, so you can just download it. I don't feel like working through it in a class, but if you're interested, it's totally good, easy to figure out. And he applies it to one of these spring matrices where you take a system where you have 3 equal weight bodies on tips of equilateral triangle. between bunch of springs, and this methodology now produces the eigenmodes and eigenvalues of the system. And I find it very cute. It's very physical. So the result of this analysis will be that there is one eigenmode in which the three bodies all go in and out over the center at the same velocity at any given moment. There is a rotational mode where they rotate this way and that way at the same velocity. And then there is this two-dimensional space, which is usually hard to understand, but he works it out very explicitly. And the two-dimensional space could be superposition of the mode where everybody is going in this direction, and twisting mode, and the other two-dimensional spaces you go in the opposite directions and you have other twisting mode. So you can get a very nice mechanical picture of what eigenmodes mean. But to understand the two-dimensional space, you have some choices of how to choose coordinates on it. So there are different interpretations. There are standing modes and there are rotational modes.
We found out P1 and P2 from the observable M, and P2 had two eigenvectors.
We assume that there are several measurements we can do on our three-dimensional systems. And one of them resolved two kinds of states with eigenvalues 2 and 3. That's the M. And then there was a second one that did something else. And when I write it down, it doesn't look like anything. But when you look at its eigenvalues, you realize that also has two possible states. The next step was to observe that these things commute. So these are two measurements I can do in any order. So I can first distinguish two subspaces using M, and then I can act on one plus two-dimensional subspace using the other guy. It could be that nothing happened. The second guy returns the same, doesn't resolve the two-dimensional space. So, so that often happens in physical applications, especially in quantum mechanics, that you have some operators, but they all nicely commute and the space doesn't get reduced. That's what happens when we are looking at our D3 group. Nothing reduces the two-dimensional space in smaller spaces. But often you can use the sequence of these observations and split stuff in smaller and smaller bits. And in this example, the second measurement actually splits up the two-dimensional space. You can do it in either order. You can use N's or M's, but eventually there are three one-dimensional spaces. And that's written in this reduction. Says there are really just, originally there was projection operator 1 and 2 that I got from M, but N split that space into two projection operators. And in this case, we are done because everybody is one-dimensional.
P2 is a combination of P4 and P5, is that correct?
That's right. That's how we got it, because this P4 and P5 were obtained by looking at a subspace 2 and finding out that the operator on subspace 2 satisfied the quadratic equation.
And because
N2 only acts on second subspace.
Right. So if
so it says that this subspace gets split into two subspaces.
So I'm trying to follow the last step of M being written in terms of P1, P4, and P5?
The very spectral resolution.
Right. So in this, yeah, so M is P1 plus 3 times P2.
Yeah.
So should we have 3 times P4 plus 12 times P5?
From this equation, it follows that P2 is this just sum that comes from here, right? P2 is the sum of P4 plus P5, because this gives me a resolution into two projection operators.
For N, why do we have?
What does this number in front means?
Yes.
This
So
is
how
a
do we?
spectral resolution, right? So these are the eigenvalues. Remember there's no reason why you should remember. M had 3 eigenvalues, 1, 3, 3.
Right.
And N had 3 eigenvalues as well. One of them was simply 4, and the other two were 1 and 4.
Okay.
And that's, the statement that's here.
Okay, understood now.
The first one was 4 on one-dimensional space. This is acting on one-dimensional space.
Right, right.
On two-dimensional space, it resolves it into two spaces.
Okay.
But M has no interesting eigenvalue on one-dimensional space because M, had this block form. It's this one. What's interesting is that suddenly you get degeneracy between something from here and something from here, because you get same eigenvalues from the two blocks. So they're not separate because you have a same eigenvalue, right? Which is not obvious when you look at it at the start. You get that on the first space, M has a trivial action. This is this eigenvalue. But on the second space, it has the same two-dimensional space, has same eigenvalue on the two projection operators. So it doesn't distinguish between them, right? But in combination, that subspace is split because the second operator distinguishes between them. I just wanted to be totally pedestrian because, there is so much indices and formalism here. So just wanted to tell you, the strategy is you make an observation and you have some number of outcomes. If number of outcomes is less than the dimension of the space, then you can only distinguish subspaces because it doesn't add up to the full space, right?
In the case of D3, when we used the third class to identify the subspaces, we got 1, 1, and 4 as the dimension. So the 4 can further be reduced. It's
done well in the books. I didn't feel like doing it. When we're doing the D3 case, we had two equations, and you can derive them for C3 satisfies its own Hamilton-Cayley equation, which is this one. And C2 similarly satisfies an equation.
Right.
And then when you use both of them, you get the full reducibility, meaning that the second guy will split this into two invariant subspaces.
So we should be looking for what C2 does to the third projection operator of C3.
Yeah, to higher dimensional spaces, because once you've gotten to one-dimensional spaces, then all observables just return a number on it, right? That's kind of obvious.
Right. Okay.
When you have a set of commuting observables, and it's a maximal set, you cannot have more than 3. That's proven in the text of this chapter for this example, or in general, the number equals number of classes. So you cannot have more detailed splitting of the space. Then you just go through it, and there are two ways. One is you learn your characters, and you use full reducibility in terms of counting how many times representation irrep shows up in your particular problem. So that's very nice, works well. You can always do this, and you can ignore the projection operators if you don't like them. Or you can construct equations for projection operators. Each one of them, each class invariance. And then that's the maximal resolution you can get of the space into reducible representation. So it does the same job. Projection operators are very explicit. If you have some explicit problem, I have a Hamiltonian, I have a set of coordinates, you can do explicit calculations and you get pretty explicit answer. And sometimes that's convenient. For example, you usually don't know when you have a triangle, what does this two-dimensional space mean? It says, I can reduce it to two-dimensional reducible subspaces, and I cannot split them to smaller bits. But what happens in these subspaces? What do they mean? The projection operator construction I find more intuitive. Look at the space as explained in the book, and it means that I have some kind of vibrational, stretching motion that is one of their, eigenmodes, and they have the same energy, but together they cover all possible motions in the subspace. And they tend to be intuitive. There could be standing modes or running modes, or you get some geometrical picture. So I find good to have these both tools at hand. You can do it by characters, you can do it by projection operators. They're equivalent. And basically, you can think of it, if you know about Fourier modes, you can solve the problem in frequency domain, or you can solve it in the energy domain. And that's what this is. You can either think of it in terms of irreducible representations, which you usually don't understand very well, or in terms of your coordinates, where you have an object doing something, which is something you can visualize, but the motion could be slightly complicated, and it's very easy to write as a sum of two frequencies or something. That's what the irreducible space gives you. It gives you a nice way of covering that subspace. I wrote a whole book just using projection operators and never using characters. So, you can publish a book. I throw in chapter 11, I notice in passing that this special, this is character orthogonality formula, it's obvious. My goal is here just to give you a repertoire of things to use if you run into a problem. Okay, so I'm kind of ready to leave general finite groups and go to physically very important examples. So I'll give you an example how you use symmetry reduction for a nonlinear system, because everything we are doing so far is linear matrices, but most equations that you will be studying in your research tend to be nonlinear. And I'll give you some feeling how it works there. It's not trivial. The nonlinear problems are very hard in terms of symmetry, but symmetry is very important. And then I'll go to something that's very important to all of us, which is translational invariance. So far, we are basically looking at rotation and, kind of wiggling in a finite space. But to formulate laws of nature, we also have to have translation in time and translation in space. That will lead us to Fourier analysis, which will be the simplest possible illustration of these both character and projection operators. So that's something that you already know, but you don't realize it all comes out of a symmetry. It's translational symmetry that makes Fourier transform look like they look.